All right, so welcome everyone to UGBS 703 Advanced Quantitative Methods, specifically the section on structural equation modeling using SPSS and AMOS. My name is Dr. Sheena L. Boateng, the L standing for Labia. I'm from the Department of Marketing and Entrepreneurship, right? And I'm also the author of the book called Structural Equation Modeling Made Easy for Business and Social Science Research using SPSS and AMOS. So if you want to brush up or you are new to all of this and you want to be able to ensure that you have an enhanced understanding, you can order one online from Amazon, or you can walk into Kingdom Bookshop on campus and you will get yourself a copy, right? It gives basics of quantitative research, from hypothesis formulation to the kinds of variables, into discussions on validity and reliability, and then straight into SEM and how you can be able to run SEM analysis and then present it in your thesis or in whatever article or paper it is that you are writing. So if you're interested, you can go ahead and purchase the book. It will help enhance your understanding of what we will be discussing in class, right? So generally, for every lecture that I have, I like to let students know the learning outcomes that we hope to achieve by the end of those sessions. And for this particular aspect of the course, we have 4 sessions. And by the end of these 4 sessions, these are the learning outcomes we hope to have achieved, right? The first one being that you, the students of the course, should be able to understand and explain the fundamentals of structural equation modeling, as well as the 2-step approach to conducting SEM analysis. So SEM is basically the abbreviated form of structural equation modeling, right? And then the second learning outcome is for you to be able to possess the knowledge and skills to perform the 2-step approach to SEM, as well as perform a mediation analysis. Now, I'm skipping a moderation analysis and performing a mediation analysis because moderation analysis is considered weak when it comes to PhD work. It is considered more rigorous in terms of quantitative research at the PhD level to have mediators rather than moderators. So given the time period that we have, I decided to go straight from testing the direct effects or the causal relationships to testing mediation analysis. And then if we have time, we can go and quickly do the moderation analysis. It's very straightforward compared to the mediation analysis, right? So these are the learning outcomes that we hope to achieve by the end of the session. Prince Yeboah, you said you also have SPSS version 22. Yes, version 22 is fine, right? Much doesn't change in the SPSS versions, right? But for the other higher order analysis software, things change significantly. That's why it's important that you have a certain version or higher. So SPSS version 22 is totally fine, Prince. Version 20, okay, I'll cap it at version 20. I wouldn't go below version 20. So Grace, version 20 is okay. All right, so those are the learning outcomes that we hope to achieve, right? So let's get straight into it. Before we start, I'd like to encourage everyone to speak up. There's no silly question. There's no weird question. There's nothing like you are going to be looked at as being less intelligent if you ask certain kinds of questions that others consider so basic. Please feel free to speak up. This is the only opportunity you have to be able to express yourself and learn the skills that you need, which will benefit you along the line. So please speak up if you have a question, and speak up if you have something you want to share or add to the discussion. Every point of view is welcome. Teresa says, did you say mediators are good for PhD? Yes, they are very good for PhD because they introduce rigor into your framework more than moderators do. So if you have a framework that you're testing, it is good for you to introduce mediators at the PhD level to be able to ensure that your research gap that you're addressing is strong and rigorous enough. Yeah. So you find that at the PhD level, people will just stick to the basic single mediator model, or go ahead and do a serial mediation or do a parallel mediation just to introduce some level of complexity and rigor, right? Moderators are basically very simple. So we don't encourage PhDs to stick to moderators. Okay, Teresa. So let's start from the basics, right? So the first question we want to ask ourselves is, what is SEM? What is the difference between a moderator and a mediator? Okay, you will learn about that as we go along, right? But a moderator is basically a variable that influences the strength and direction of a relationship. So if you introduce a moderator into a model, the only effect it can have is to either strengthen the direct relationship between an independent and a dependent variable, which we are going to learn what they are very soon, or weaken that relationship. Whereas a mediator is an intervening variable, right? That inserts itself in the relationship between an independent and a dependent variable, such that for the independent variable to have an influence on the dependent variable, it has to go through the mediating or intervening variable, right? And in instances where the independent variable can on its own influence the dependent variable and at the same time influence the dependent variable through the mediator, we refer to that as a partial mediation. Whereas if it does not influence the dependent variable on its own, but it does so through the mediating variable, we refer to that as a full mediation. So that in a nutshell is the difference between a mediator and a moderator. So by the explanation I gave alone, you can see that the mediator has more of a prominent role because it can insert itself in the middle of that direct relationship and cause change. Whereas a moderator cannot insert itself, it can only influence the direction of the relationship by either weakening it or strengthening it. So Benjamin, I hope that basically explains it for you. Good. All right, but we will hear more about mediators as we go along. Okay, so let's start from the basics, right? What is SEM? SEM is the abbreviated form of structural equation modeling, which is a multivariate data analysis technique that involves simultaneously estimating and testing a series of hypothesized interrelated dependency relationships, right? That's a lot of words. So let's take them one after the other, right? So we are talking about simultaneously estimating, meaning that it tests a number of direct relationships at the same time. Are we good? Now, the other word we have here is series of hypothesized interrelated dependency relationships, meaning that in any SEM model, you will have a series of direct relationships, which you have hypothesized for, right? But all of these direct relationships are tested at the same time because of their interrelationships. So you will see that in the SEM model, we have different independent variables and then perhaps one or more dependent variables influencing each other using various direct causal relationships, right? And that is what we test when we do structural equation modeling. Now, these relationships are tested often between a set of latent constructs, right? So when we talk about latent constructs, we are referring to the actual variables of interest in your study. So for instance, if you want to test the effect of online customer engagement, right, on customer loyalty and customer engagement are our latent variables. And they are also referred to as unobserved variables or unobserved constructs, which we will see graphically very soon. Now, in quantitative research, once you identify your variables, you develop measures or statements that help to measure these variables, and you put them together in a questionnaire and you collect data, right? Now, these statements or measures that you use to measure each of the variables that you have identified or your variables of interest in your framework are what we refer to as the manifest or observed variables. So the variables of interest to you, for instance, being online engagement or customer loyalty, are your latent unobserved variables. And then the independent statements that you use to measure each of these variables in your questionnaire are what we refer to as the manifest or observed variables. Please, does it make sense?
Yes.
Good. Now, it's very important you get this concept of latent or unobserved and manifest or observed variables because that is the concept that AMOS thrives on, right? So in every AMOS graphic, you will be able to pick out the latent variables and the manifest variables, which will be able to help you to come up with the perfect model that fits the data that you have gathered. Okay, so now that we have understood what SEM is, let's look at why SEM. right? Because I've had this question being asked before in one particular forum that I was sitting in regarding quantitative. Why shouldn't I do multiple regression and call it a day, right? Why shouldn't I do a logistic regression and call it a day, right? Now, the choice of a particular analytical technique depends on the nature of your research objectives and your research questions. So you need to be able to understand the relationships between your variables and the objectives of your study to know which particular statistical technique will be relevant to it. So if your objectives do not call for SEM, you can't force SEM on your objectives. If your objectives call for a logistic regression, that is what it has to be, right? So you need to be able to, first of all, understand the kind of research objectives that you have to be able to know the multivariate data analysis technique that will be relevant to it, right? So in the event that based on your objectives, SEM is relevant, it is most likely going to be because, one, SEM facilitates the discovery and confirmation of relationships among multiple variables. So with SEM, you can test multiple variables at a time and also test their interdependencies and the interrelationship that exists between them at the same time. That's one of the key characteristics why SEM is applied most often in social science research, because we know that in social science research, there's always a multiplicity of variables that are influencing a certain phenomenon. So SEM helps us to be able to put all these different variables together and test them as they react in each other's presence, right? Another thing we can talk about for why SEM is that it incorporates abstract and unobservable constructs, right? Which are measured by indicators called items. So that means that even if you do not know exactly what a particular variable of interest entails to you, you can be able to use the concept of the latent or unobserved variable and the observed variable to come close to measuring this particular variable of interest to you, right? And with SEM, you can analyze this and be able to come up with the best set of observed variables that represents that particular latent variable that you are interested in. Another thing is because of the fact that SEM can simultaneously model relationships among multiple predictor and criterion variables. Now, predictor or criterion variable is another name for independent and dependent variables, right? So please learn them. If I say exogenous variable at some point, I'm referring to an independent variable. If I say endogenous, right? It means the dependent variable, which is usually on the end of the equation, right? So learn the various terminologies that we use to refer to these variables. Okay, so still on the issue, why SEM? Again, the intricate causal networks that are enabled by SEM characterize real-world processes better than simple correlation-based models. Like I just mentioned a moment ago, in social science research, we are dealing with human behavior and phenomena that are always influenced by a multiplicity of factors. And SEM gives us the ability to test the interactions between these multiple factors to come up with actual explanations that are plausible to explain how those phenomena are occurring or taking place, right? Now, this particular characteristic of SEM makes it differ greatly from most of the first generation multivariate data analysis techniques that we know of, like the linear regressions and the logits and the ANOVA and the MANOVA, all of which help us to be able to test different things when it comes to quantitative data. Can it give you the cause of the relation? Yes, SEM basically tests causality. So it can tell you whether a particular variable predicts another. In this case, does the independent variable predict the dependent variable? And how does it predict it in terms of moderators and mediators? And then it can also tell you how the variable differs in terms of different groups. So you can run a multi-group analysis as well in SEM. How different is SEM from regression? Okay, so SEM is able to test multiple equations at a time, right? So you can test various variables. Thank you, Doc. So you can test multiple equations at the same time. You know, we have the basic regression equation, which is linear in nature, right? And we can only test one linear relationship at a time, looking at a dependent variable and a number of independent variables that influence it. With SEM, you can take about 4 or 5 of these linear regression models and put them together and run them at the same time, right? So that's how SEM differs from regression. Regression is just one linear model at a time. SEM can run multiple linear regression models at the same time. So I hope that answers your question, Abdul Karim. All right, so now that we know why we use SEM, let's look at the different types of SEM that they are, right? Now, there are 2 main types of SEM. Okay, so the independent variable and the dependent variable are both latent variables because they are unobserved. Unobserved in the sense that we do not know the actual set of items or measures that come together to represent these 2 variables. So they are all latent. So the latent variable can be both independent or dependent, as we will see very soon. It is expressed better in graphical form. So Clement, hold on for a moment, and then as we go along, when you see it graphically represented, you'll be able to understand the concept of the latent variable and how it can be both an independent and a dependent variable. Okay, so like I was saying, there are 2 main types of SEM, right? We have covariance-based SEM, also known as factor-based SEM or maximum likelihood-based SEM. And these ones can be carried out using a specific set of software, including AMOS, Lizerel, M+, and EQS. So if you are using any of these software to run structural equation modeling, you are using the covariance-based approach because that's how they are wired to function. Then we have the variance-based or the components-based approach, or more popularly called the partial least square SEM, right? Which is carried out using software programs including Adanko, PLS Graph, Smart PLS, and Excel Stats, right? So if you are using any of these software, then you know automatically you are doing what we refer to as variance-based SEM. Now, AMOS, which we are using for our purposes today and for the remainder of our sessions, is a covariance-based SEM software, right? So it has its own limitations, which we will discover very soon in terms of the difference between variance-based and covariance-based SEM. So let's look at the differences between the 2, right? How do covariance-based SEM and variance-based SEM differ from each other? First, we can talk about the fact that covariance-based SEM focuses on minimizing the difference between the observed and estimated covariance matrices, right? Please don't get confused. When we hear some of these big words, especially those of us who are new to Quanti, we become scared, right? So I just try to encourage you to know it for what it is, but don't beat yourself up if you can't remember or fully appreciate it. It will make sense very soon. So in as much as the covariance-based SEM focuses on minimizing the differences between the observed and estimated covariance matrices, variance-based SEM focuses on maximizing explained variance of the endogenous constructs, right? And this is basically looking at how to maximize the predictive ability of the model. So in that regard, when you're running variance-based SEM, one key measure that comes up all the time is the R-squared. And here the R-squared in variance-based SEM is more prominent than in the covariance-based SEM, right? Where they emphasize more of the R-squared in conjunction with other measures like model fit, which we will talk about very soon. Also, for covariance-based SEM, it is more applicable to testing existing theory, right? So it plays more to confirmatory analysis, right? Unlike the variance-based SEM, which is more applicable to testing existing theory, at the same time to developing theory. So you can be able to use it for both confirmatory analysis and exploratory analysis. That is why for software like AMOS and Lizerel that deal with covariance-based SEM are prone to the use of large sample sizes, right? Because they are more of a confirmatory software that help us to confirm theory that we have identified in the literature. But the variance-based SEM can do both, help you to confirm theory as well as explore. And because of that, the variance-based SEM can handle small sample sizes, like a minimum of 50, and you'll be able to run a good variance-based SEM and get output that is to a large extent reliable, right? So that's another difference between covariance and variance-based SEM. right? So in essence, we have talked about the sample sizes, and they flow directly from the reason I just gave. Because of the confirmatory nature of covariance-based SEM, they prefer more large sample sizes. Whereas with the combined exploratory and confirmatory nature of variance-based, they rely more on smaller sample sizes, but it could also work with large sample sizes, right? Now, another difference between the two is that covariance-based SEM requires that the data must be normally distributed. So if your data is not normally distributed and you run covariance-based SEM, it is highly likely that you will have the giggle effect, which is an acronym for garbage in, garbage out, right? So you want to make sure that your data is normally distributed if you plan on using covariance-based SEM, right? But for variance-based SEM, it can handle both, right? If the data is normally distributed or non-normally distributed, variance-based SEM can handle it, right? Now, this to someone may be a limitation, but because of the requirements of normally distributed data, it makes covariance-based SEM very rigorous. So if there is no theoretically proven or theoretically valid relationship between your constructs, covariance-based SEM will expose you. Whereas if the relationship is there, but it's not very strong or has not been proven yet, variance-based SEM can help you to be able to establish a baseline. That is why it supports both exploratory and confirmatory, right? James, you said, must all these requirements be met before one determines which type of SEM to use? Technically, yes. Because if you know the theory backing your model is weak, I will not encourage you to go for covariance-based SEM, because then your outputs will be a bit tricky to achieve because it has a lot of requirements that you need to be able to meet, right? Whereas with variance-based SEM, if the theoretical relationship between your variables is not so strong, but you can see there's something there, you can take the exploratory approach and try to develop this theory on your own using the variance-based approach, right? So you need to be able to understand the kind of model that you have, its theoretical backing, and then there's the data that you are working with to be able to know which approach or technique best fits what you're doing. And then finally, we can talk about the fact that in terms of the measurement model and the nature of the variables and constructs that are measured, variance-based SEM can handle both reflective and formative measurement models, whereas covariance-based SEM can only handle reflective measurement models. And I'm going to break this down in the next few seconds. So let's look at this model for a second, right? So the one who asked the question about the latent and independent variables, right? So we can see from the model here that X and Y are both latent variables or unobserved variables, in the sense that they are the variables of interest to us, but we have not been able to prove or test the actual set of measurement items that come together to constitute these two variables. And that is why they are unobserved. Now, to be able to come to an appreciation of the set of measures that represents these unobserved variables, we use what we call the measurement items, which are the observed variables. So you can see that here, the exogenous or the independent variable and the endogenous or the dependent variable both qualify to be latent variables because they are both unobserved, whereas they have a set of observed variables each, right, representing them that we are going to test to be able to prove or disprove. Now, once we have been able to establish this, let's come to the issue of formative and reflective models, right? So when we talk about a reflective model, the main difference between the two, being formative and reflective models, is that when we look at the diagram, the path diagram causal arrows go from the latent variable to the indicator variables in a reflective model. So let's look at that very quickly. Can we see the reflective model here? The arrows are pointing from the latent variable X outward to the individual observed variables. Please, can we see that?
Yes.
Good. So that is characteristic of a reflective model. And that's generally the one that we have been testing in Quanti all the time. Reflective models are very popular, right? For reasons that we will learn about very soon. Okay, Alex, right now you are veering us off track. So hold on to that question. We'll discuss it later after the class, right? And then let's just focus on our SIM model here. Okay, so as we have established in the reflective model, the arrows point outward, moving from the latent variable to the observed variable, right? Whereas with the formative model, the causal arrows go from the indicator variables to the latent variables. So can we see that it's the reverse for the formative? We have the arrows pointing from each of the single observed variables towards the latent variable. Please, can we see that?
Yes, please.
Yeah.
Yes,
Good. And there's a simple explanation for that, right?
Yeah.
The arrows are pointing from the individual indicators or observed variables to the unobserved variable because the latent variable is composed of these independent measures, right? So these three measures are the cause of this variable. So as someone will say in tree, they always go together because together they are the cause of Y. Please, does it make sense?
Yes.
Good. But with the reflective model, the measures are representative of the latent variable, meaning that there are other variables too that could probably be representative of the same latent variable, right?
Okay.
So we say that the indicators are a manifestation of the latent variable such that you can interchange them with any other variable that you believe is a manifestation of X and it will fit. Please, does it make sense?
Okay. It makes sense.
And because of that, in AMOS, when you are dealing with reflective models, you can delete variables and reintroduce new variables at any time. Whereas with a formative model, you can't do that. I hope that makes sense.
Yes. Yes, please.
Yes. Okay. Now, the introduction of a reflective or formative model, once again, I want to emphasize, is based on theory. So if the theory that you have read, that's why you have to have a strong grasp of the literature, right? And know the gaps in your field and know which variables relate to each other, which variables cause each other, which variables mediate, so that you can be able to tell where you have to use a formative model and where you have to use a reflective model. Please, I hope that makes sense.
Yes.
Good. Now, still on the differences between the two, we can also talk about the fact that the reflective model, the indicators that we see in there collectively are a sample of all the possible indicators of that particular reality. So like I was saying, you can interchange the variables at any time, provided you have captured them as part of your data set, to be able to determine which ones are the perfect set of variables that are a true reflection of that reality you are trying to measure, right? But with the formative model, all the indicators you have there, being the Y1, Y2, Y3, are all the indicators that collectively represent the dimensions of this latent variable Y. So if together they come together to form Y, you can't take one out, because the moment you take one out, you have lost the essence of Y. And because of that, we do not have formative variables in AMOS, because with AMOS, we do a lot of what we call trimming and model modification to be able to ensure that we get the best fitting model to explain the phenomenon that we are studying, right? But you can use formative models in Smart PLS because it is more exploratory. So it gives you freedom to be able to apply the different versions of the phenomenon you are trying to study, either in the form of a reflective model or a formative model, right? So that is it for the differences between reflective and formative models. Please, do we all understand thus far?
Yes, look.
Does the formative model relate only to the dependent variable? No, Abdul Karimu. I'm just using the dependent variable here for the purposes of illustration, but the formative model could also be an independent variable. I hope that answers your question. Good. So you can have a formative independent variable and you can have a formative dependent variable. The same way we have a latent independent variable and a latent dependent variable. Okay, any questions thus far? All right. Now, the reason why we are going to focus on covariance-based SEM for this particular discussion is that covariance-based SEM is easier to achieve, especially with regard to the kind of research that we do, which is mostly backed by theory. right? But in a few instances, you may be doing your PhD in an area where it requires for you to have a good balance of both the formative and reflective models to be able to explore the area that you are studying, given that perhaps that area is a bit under-researched and there's not so much theory that you can fall on in that area, right? But another major reason is the fact that the Smart PLS software compared to the AMOS software is more difficult to come by. So Smart PLS gives you a trial version initially when you sign up, right? But once that trial version expires, you need to be able to buy the full version. And the software is designed such that they give you a unique independent key to be able to use to access the software. So when you buy it as a person or you subscribe to it as an individual, you can't share your key with anyone else. You can only use it for yourself on one device, on one computer, right? And when it expires, you have to renew it. And it's quite expensive. Let me add that. But for AMOS, once you get the product key, you can be able to share with other people. And when you get the license, you can install it on more than one device, right? So it makes AMOS more of the preferred software to use than Smart PLS. Previously, Literal was also very popular, but Literal is a bit more cumbersome to use compared to AMOS. AMOS is more click-based, just like SPSS, whereas Literal, like Stata, is more command-based. So it's a bit complex for people who do not have a strong quantitative or mathematical background to use, right? So that's another reason why we will focus on AMOS and covariance-based STEM. However, on your own, if you want to learn how to use any of them, you are free to do so. Because personally, I started with Literal, right? So I mastered Literal, then I moved on from Literal to AMOS, and then I moved on to Smart PLS. And I have publications using all those different kinds of software. So it's up to you what you have access to and what you're comfortable using, right? To be able to help you achieve whatever objective you seek to achieve with the analysis you're going to run. Please, I hope that makes sense.
Yes.
Okay. So let's go straight into covariance-based SEM, right? Which is what we are going to focus on. So like we have already established, this type of SEM involves maximum likelihood analysis, right? So the AMOS that we will be using maximum likelihood estimation, right? To estimate a set of model parameters so that the theoretical covariance matrix implied by the system of structural equations is as close as possible to the empirical covariance matrix observed within the estimation sample. Please, once again, these are very technical, huge words. Don't let it scare you. Just appreciate it for what it is, and then we can move on. You don't have to understand everything about this at this point, right? It's just good enough for us to know that this is what covariance-based SEM is. Now let's move on to conducting covariance-based SEM, right? Now, the most popular technique for conducting SEM analysis, be it covariance-based or variance-based, is the two-step approach, right? And with the two-step approach to SEM, it was postulated by Anderson and Jervin in 1988, right? And it's also referred to as the incremental approach, where we move from one stage to another. And it involves two main stages. The first stage is what we refer to as the measurement phase, where we are specifying a measurement model which shows how the individual variables relate to their indicators. Remember, we talked about the latent variable and then the observed variable. Please, do we remember?
Yes.
Good. So in performing the measurement model, in estimating the measurement model, sorry, using the confirmatory factor analysis, we are basically trying to see how these individual observed variables relate to the latent variable. So this is where we are trying to determine the optimal set of observed variables that represents the latent variable that we are trying to measure, right? And that is what we refer to as a confirmatory factor analysis. So in AMOS, in running the confirmatory factor analysis, we do some modifications, some pruning to be able to ensure that we end up with a set of variables that meet all the required criteria to represent the complete set of measures that we are going to use to represent our latent variable moving forward into the next phase. And this next phase we are talking about is referred to as the structural phase. And the structural phase is where you conduct a path analysis to test your structural model. So at the confirmatory analysis stage, your measurement model does not have any of the causal parts, which shows us how the independent variables relate to the dependent variables. At that point in time, all of them are independent variables. There's no variable that is delineated as a dependent variable at that point. But when you get to the structural phase, you now have to introduce the causal parts to let us see which variable is dependent and which variable is independent, for us to determine how they influence each other. Now, the introduction of these parts and the analysis that we do to be able to determine whether these parts are significant or insignificant is what we refer to as a path analysis. Please, does it make sense?
Yes, please.
Yes, please.
Okay, so at least there's at least two people in the room. Because we are not using our reactions.
Making sense, Doc.
I can't hear you, I can't see your reaction, so I don't know if I'm by myself.
Doc,
Yeah,
can
with
you
you,
please
Doc.
go over that
We
point?
are with you, Lavia.
Okay.
Can you please go over that point, the second stage?
Where?
Second stage, structural phase.
Okay. So the structural phase is where you have been able to establish what your latent variables are and the specific observed variables that represent them, right? So usually in SEM analysis, you will start with a set of observed variables. You can have like 5, 6, 7 of them. But by the end of the confirmatory analysis, sometimes you will end up with 2 or 3, right? Because at that point, those are the variables that the analysis has helped us to confirm are the actual measures of each of the latent variables we are talking about. So once you know which measures represent each of your latent variables, you can now go ahead and draw the causal paths between each of these variables because they relate to each other per your research framework. Please, does it make sense? So you will now introduce those parts to tell us which one is an independent variable and which one is a dependent variable. Yes, you test significance only with path analysis. That is in terms of the direct relationships. Okay. You can perform path analysis using multiple regression as well. Only that you can only do it in a linear form. So you can be able to tell how each of them relate to each other, right? But with SEM, you can be able to test multiple paths at the same time. And that is what makes SEM unique. Right? So for the path analysis, you introduce these individual paths representing these relationships. And then when you do so, you are able to determine which direct relationships are significant and which ones are not. And at this point, with the path analysis, all you can test is direct causality. Right? So the two-stage approach to SEM ends with the test of the direct paths. Can you trim indicators down to 1? No. Because in SEM, you need to have a marker variable, especially when you are using Lizrael or AMOS. So if you trim to 1, that is the only variable left. And you can't use just a marker variable to represent an entire latent variable. So once you trim and you're left with 1, you have to delete that entire variable from the model. Roxanne, I hope that makes sense.
Yes, Doc.
Good.
Thank you.
Good. Right. So for AMOS, you can't end up with 1. The minimum you can end up with is 2, where 1 will be the marker variable and the other one will be the corresponding variable. Right. So the two-stage approach ends with path analysis, where you test direct relationships. So afterwards, if you want to do any higher order forms of analysis, you need to apply different analytical techniques. So if you want to do a mediation, you need to go ahead and test what we refer to as a mediation analysis. If you want to introduce moderators, you need to go ahead and conduct the moderation analysis, right? So in presenting your analysis results, you present each of these phases in different sections. You present phase 1 in a different section, phase 2 in a different section, and then whatever additional forms of analysis you perform, you present them in different sections as well, right? So at each phase, there are certain measures that you need to be cognizant of. And there are certain tests that you have to perform. And until you have performed those tests and met the requirements of all these tests, you can't proceed to the next phase. Now let's start with the measurement phase. When you are at the measurement phase, you perform what we refer to as, what analysis do we perform at the measurement phase? Can someone quickly remind us? What analysis do we perform at the measurement phase? What analysis do we perform then? Yeah.
Confirmatory factor analysis.
Yeah, a confirmatory factor analysis, right? So Gabriel, your hand was up. You have the floor.
Yeah, I was going to answer the question.
Okay, so a confirmatory factor
question.
analysis. Okay, thank you, Gabriel. So a confirmatory factor analysis, right? And as part of the confirmatory factor analysis, you are conducting several tests. The first set of tests is the reliability test. And the measures you need to be able to determine that this test has been successfully completed and all the requirements have been met are, first of all, the Cronbach's alpha. I believe we've all heard about the Cronbach's alpha, right? Good. So the Cronbach's alpha is the most basic test of reliability. Once you have satisfied the criteria for the Cronbach's alpha, please, what's the cutoff point for Cronbach's alpha? What is the acceptable threshold for Cronbach's alpha? Grace,
1%.
go ahead.
I think from 70.
From 70. Please
Yeah,
clarify.
I mean 0.7.
Okay. That's one threshold, right? Any other perspective? Teresa, yeah, go ahead.
0.6.
0.6, good. So from what I know, some thresholds give 0.7 and some give 0.6. Now with quantitative data analysis, there's something we all need to remember. It's all about process and what is acceptable and not acceptable based on literature. So for every measure that you accept or reject, you need to provide literature justification for. So some literature provide that the Cronbach's alpha cutoff point is 0.7. Others, it's 0.6, especially if you are using our basic quantitative books like Hare et al. So Hare et al. Gives us the basic 0.6, right? So depending on what source you are citing to justify your cutoff point, with Cronbach's alpha, you may end up with a 0.6 or 0.7. Please, are we okay?
Yes, Doc.
Good. So once you can establish that the Cronbach's alpha for all your measures have reached the 0.6 cutoff point, you now go ahead to test for composite reliability. Please, does anyone know composite reliability or the CR? Those of you who have done SIM before. Composite reliability. Has anyone heard of composite reliability? Gabriel, you have done SIM before. What is the composite reliability? Gabriel.
Hello?
I'm here, Gabriel. Tell us, what's composite reliability about?
Okay, so composite reliability is practically trying to check whether the measurement items maps correctly or actually explains correctly the construct or the latent variable that it is supposed to explain.
Are you sure? Are you very sure?
That's what I remember. Yes.
From composite reliability.
Mm-hmm.
Okay, any contrary view? Any contrary view of what the composite reliability is? CR is equal to internal consistency. That's a very succinct way to put it. The measure of internal consistency among scale items, exactly, right? So generally that is it, you're all right, right? However, in terms of comparing between the convex alpha and the composite reliability. The composite reliability is a bit more rigorous than the convex alpha. And that is why, in addition to the convex alpha, we have to test for the composite reliability. So what is the cutoff point for the composite reliability? Okay, Theodora says 0.7. Gabriel, do you concur?
Yeah, I concur.
Good. So the composite reliability has to be greater than or equal to 0.7 for each of your variables, right? Next, we have the average variance extracted, or the AVE, right? So what does the AVE stand for? Gabriel, do you want to take a shot at this one, or you want to pass it along? Gabriel.
I'll give someone the chance to answer this.
Okay. So what is the AVE? What is average variance extracted? Anyone? Okay. So the average variance extracted basically assesses the amount of variance captured by a factor or construct as compared with the variance that occurs due to random measurement error, right? So the average variance extracted is another measure of reliability or internal consistency. So what is the cutoff point of the average variance extracted? What is the cutoff point for the average variance extracted? Anyone? Average variance extracted. Hey, where are those who said they've done SEM before? Theodora, what's the cutoff point for average variance extracted?
0.5.
A minimum of 0.5.
Exactly, a minimum of 0.5. So that's the cutoff for average variance extracted. So anything from 0.5 and above, we accept, right? So once we have satisfied our internal consistency or reliability, we now have to go ahead and test for convergent validity. So when we say convergent validity, what do we mean? When we say convergent validity, what are we talking about? Okay, Theodora, go ahead. Theodora, your hand is up. You may go ahead.
We are looking at how the indicators for each of the constructs correlate with one another.
Good.
Hello?
Yes, Theodora. Good. So that's
Yes.
convergent validity, right? So basically, we're trying to see how they correlate with one another or how they go together, right? So in this case, for measuring convergent validity, we start from the factor loadings, right? And what's the minimum threshold for factor loadings?
0.30.
Okay, that's like the base minimum. But in SEM, if you go for a 0.30, you're asking for trouble because already it means that the correlation is very weak. Are you with me?
Yeah.
And when you have a very low factor loading like that, it can affect your average variance extracted. So even though 0.3 is acceptable, we normally push for higher factor loadings, right? So apart from 0.3, is there any other threshold that we know is applicable when we talk about
Yes.
factor loadings?
0.5.
0.5, right? Because that is fairly strong enough to help us to be able to have a solid model that will satisfy the criteria that we are expecting it to. Right? So factor loadings of 0.5 are desirable, even though they can go below. With structural equation modeling specifically, especially in AMOS, we stick to factor loadings of 0.5 and above. So any measure that has a factor loading of less than 0.5 has got to be eliminated. Okay. Now, as part of convergent validity, we once again rely on our composite reliability and our average variance extracted. right, to be able to establish convergent validity. And this is once again because of the level of rigor that they involve in terms of helping us to be able to determine the amount of variance between the factors that we are measuring and whether or not they actually measure what they are supposed to measure. So once we have been able to satisfy internal consistency and reliability, and we have been able to satisfy convergent validity, the next level is to satisfy discriminant validity. And here, to satisfy discriminant validity, there are two main measures that are of importance to us, which we apply in two separate techniques to establish discriminant validity, right? So to establish discriminant validity, we use the average variance extracted, as well as the correlations between the variables or the constructs, right? And we put these two together to be able to determine whether there's discriminant validity in the model that we have estimated using two main techniques. There's a very popular one. Who knows that very popular one? There's a very popular test of discriminant validity that almost everyone uses. See, those of you who have used them before, Solomon, or they appear.
What is structural equation modeling?
No, I think that's the funnel lacquer.
Hold on, please. We said we were going to do this in an orderly manner, right? Solomon, are you there? Please, another thing, no one is allowed to ghost in this class because I can randomly mention any name at any time. Solomon, are you there?
Yes, Doc, I'm here. Doc,
okay.
That's the funnel lacquer.
That's the what?
Cast was mentioned already.
That's the what?
Funnel and lacquer.
Funnel and lacquer, good. Right?
Hello, Doc.
Yes, I can hear you.
Yes, Doc, funnel and lacquer.
Good, it's funnel and lacquer. So Roxanne, it's not funnel, lacquer, hyphenated, right? And that's another thing that irks me, especially when I review quantitative papers or quantitative work. You need to be able to get the names of these statisticians that you are quoting right? So funnel and lacquer are two separate people. You can't hyphenate their names. So if you are saying the criterion is the funnel and lacquer, there's an R in the name. So please learn how to spell the names of these statisticians you are quoting properly, right? So it's Funnell and Lacquer, 1981, right? That's the citation for the Funnell and Lacquer criterion as it's applied today. And that's the most common one, right? However, quantitative data analysis has been evolving, and the same goes for SEM. So in recent times, they have identified that the Funnell and Lacquer criterion is a bit strict in terms of determining discriminant validity, right? And it's not always fully accurate, depending on some scholars. So a new technique for determining discriminant validity has been introduced to be able to support the Funnell and Lacquer criterion. So you realize that some people will go ahead and use just that new technique or combine both the Funnell and Lacquer and the new technique in one analysis to be able to ensure that they have covered all the fronts as they relate to discriminant validity. So who knows of this other technique, apart from the Funnell and Lacquer criterion? Who knows of this other technique? The other technique for determining discriminant validity. Anybody? Gabriel, your hand is up. Yeah.
The HTMT ratio.
Good. So HTMT stands for? Gabriel, what does HTMT stand for?
Hetero-trait monotrait ratio. Yeah.
Yeah, so hetero-trait monotrait ratio of correlations, right? And it's not enough to just state the technique, right? You also need to be able to cite the source to back up your technique, because everything we are doing is scientifically based. Please, are you with me? Please, are you with me? Hello?
Yes, Doc.
Good. So you need to be able to state the theoretical backing for every technique or scientific choice that you make. So if you are choosing Funnell and Lacquer criterion, then you are doing it based on Funnell and Lacquer 1981. If you are doing HTMT analysis, which refers to the hetero-trait monotrait ratio of correlations, then you are talking about Hensela et al. 2015. Please, are we all understanding?
Yes, Doc.
Good. So these are the two main techniques that you can use to test for discriminant validity, right? And once you have been able to do so, the next thing you do is to be able to assess the model fit indices. And these indices basically help you to be able to determine whether the model that you have is a good fit for the data that you have gathered, right? So in performing SEM analysis at the measurement phase, you go through each of these tests simultaneously, one after the other, to ensure that you satisfy all the criteria at each of these stages. So in our practical sessions, we will be demonstrating how to perform each of these using AMOS, so that you will be able to perform them. Now, the HTMT analysis, you can perform in AMOS using a plugin, or you can do it manually in Excel. And I'll do my best to teach you both techniques. Please, are we okay?
Yes.
Okay.
Yes, Doc.
So that is it for the measurement phase.
Yes.
Right? So we have basically talked about all the measures that go into each of the phases. We have the internal consistency and reliability phase, where we have the Cronbach's alpha, the composite reliability, and the average variance extracted. And each of them have their own cutoff criteria, which must apply in our analysis. Then at the convergent validity stage, we also talked about three main measures, right? The factor loadings, the CR values, and the AVE values once again, to help us to be able to determine whether the variables that we have, right, share a high amount of variance in common. Do they actually measure what they say they measure, right? And then we also talked about discriminant validity, where we are performing specific tests to be able to determine the degree to which a given construct is clearly distinct from the other constructs in your framework. Because if they are not distinct, we cannot be able to clearly determine how they influence each other, right? And for that, we use the Fornell and Lacker criterion by Fornell and Lacker 1981, or the HTMT analysis by Hensela et al. 2015, right? So we will practically be demonstrating each of these in our practical sessions. Now, with each of these stages that we go through, being it determining reliability, validity, and discriminant validity, there are ways in which we have to present the output, right? So let's look at a typical table presenting the output of a measurement phase, where we did a confirmatory factor analysis. Please, can we see the slide I'm sharing?
Yes, please.
So
Yes.
here, the entire outcome of the measurement phase, being the confirmatory factor analysis, is summarized into one table, right? So in the table, we have the individual variables or the constructs, and then the items that measure them. And for each of the items, we have their factor loadings in the columns provided here, right? And then we also have the alpha values, or the Cronbach alpha values, for each of these variables. Then we also have the CR, right? So the CR is basically the T value as presented in AMOS. So if you see CR anywhere, it refers to the T value. Can you have the slides? You will definitely get your hands on the slides, but please focus on understanding what is being taught first. I hope that's okay, Pekwamako.
Yes, Doc.
Okay, so as part of the measurement phase, we conducted a confirmatory factor analysis, and the output of that confirmatory factor analysis is what we have presented in this table form, right? So we have the factor loadings here, we have the Cronbach's alpha values, we have the CR, right? Here, it can either be the composite reliability or the T values, right? So generally, some people will present both the T values and the CR and AVE values, but it's all up to you. Most of the time, the particular outlet for the analysis you are running determines how you present some of the tables and the specific measures that you present, right? So usually if you are writing for a particular journal, I advise that you get a sample from the journal and see how they present the output from analysis of a similar nature to know what items to include in your tables. But in other words, if it is for your long essay, you can decide, or your thesis, you can decide what measures to introduce. But there are some basic measures that have to be present. And for the measurement phase, we need to see the factor loadings, we need to see the Cronbach's alpha, we need to see the CR values and the AVE values, right? Which will tell us about the internal consistency or the reliability. And then it will also tell us about the convergent validity. Now, when it comes to discriminant validity, it's a bit of a different story because you have to run a different set of analysis to be able to test for the Fornell and Lacker criterion, as well as the HTMT ratio of correlations. And again, the output from these are also presented in separate tables. So the Fornell and Lacker criterion is presented in a separate table that has its own format with footnotes. And the same goes for the HTMT, that is also presented in a separate table that has its own format and footnotes. Eric says, is there a minimum or maximum number of attribute statements to use? In terms of the number of individual statements that measure a variable, if that is what you mean. There's no minimum, right? But there's such a thing as having too many variables. Because if you have too many items measuring your variable, it will be a lot for the software to digest and process. And the more variables you have, the more you dilute the measurement of your latent variable, because it is having to determine out of this whole lot which ones are actually more reliable measures of the variable that you have. So I usually recommend between a minimum of 4 or 5 items per variable to start with, so that if you collect your data and you run your analysis, depending on how the analysis goes, even if you lose about 2 or 3 of them, you will still have the minimum 2 that you need to be able to proceed to the structural phase. So there's no minimum or maximum, but I don't recommend having too many items measuring a variable. I recommend you cap it at most 8. That way you can be able to ensure that you have a reliable set of measures that will definitely end up being good representations of the latent variable that you're trying to test. Alex, you said, is it the case that SEM is only used for primary data? Yes. But you can also use it for secondary data, depending on how the secondary data was collected and how it was measured. So if the secondary data was collected in a manner that allows you to use SEM, you're free to do so, right? But if the manner in which it was collected, which again brings me back to the issue of the various types of SEM, being variance-based and covariance-based SEM, right? I always tell students that structural equation modeling starts from when you select your variables to when you design your questionnaire. So depending on how you design your questionnaire and how you measure your constructs, you may or may not be able to use SEM to analyze them. So it all goes back to how the data was collected. But generally, we prefer primary data because with primary data, you are collecting this for a specific purpose. So you have the opportunity to design the questionnaire the way you want and make sure that it is designed in a manner that will give you data that you can analyze using SEM. Okay, so Eric says, what about mixing negative and positive attributes? Is that okay? You can mix negative and positive, but encoding them and entering them into the data, they must all move in the same direction. So if you have negative and positive attributes or items mixed together, you have to reverse code. If most of them are going in the positive direction, you have to reverse code the negatives to read positive. But you will know where they are because all the variables have to move in the same direction for you to be able to analyze objectively. Please, I hope that makes sense. Okay, cool.
Yes.
All right. How will you know the variable selected can be used under SEM? Okay, so SEM generally deals with continuous variables, right? And categorical variables. So you can have a categorical variable that you can use for SEM, and you can have a continuous variable that you can use for SEM. The only difference is that if you are using a mixture of categorical and continuous variables, you cannot test for discriminant validity and convergent validity and reliability on a categorical variable, right? Because it is not on a scale. This doesn't make sense. So you can only test for reliability and validity on continuous variables. So if you have a categorical variable as part of your SEM analysis, you just need to indicate that it is part of the analysis and it was measured using these categories, but you cannot test for its reliability and validity. Please, does it make sense? Okay, Teresa says yes. So I believe you're good. All right. So in essence, this is the measurement model and how it will look like, right? Now, for the Fornell and Lacker criterion and the HTMT analysis, I mentioned that they are also presented in separate tables. So this is how a typical discriminant validity measured using the Fornell and Lacker criterion will look like in table form, right? So we have all the individual independent variables presented, and then the intercorrelations between them presented. And then we have on the diagonal in the middle, where we would have had ones all across because variables correlate perfectly with each other. On that line diagonally, we have the AVEs. And these AVEs, depending on the Fornell and Lacker criterion, can either be squared, right? We have to square one of the two, either the interconstruct correlations or the AVEs. So under the table, we can see the footnotes, right? It says diagonal elements are the square root of the variance shared between the constructs. So you either find the square root of the AVE and place it on the diagonal, or do the reverse. Leave the AVEs as they are and then square the interconstruct correlations. Please, does it make sense? Please, does it make sense?
Yes, please.
So for the Fornell and Lacker criterion, let me go over it again. For the Fornell and Lacker criterion, we are dealing basically with the AVEs and the interconstruct correlations. So the correlations between the individual variables or constructs that we have. So Fornell and Lacker tell us that if we want to determine discriminant validity, the AVEs should be larger than whatever you have in between the variables by way of correlation. So whatever you have on the diagonal, right, should be larger than the interconstruct correlation. So you can either decide to find the square root of the AVEs and put them in the diagonal and leave the correlations alone, or leave the AVEs alone and square the interconstruct correlations. Either way, whatever is on the diagonal should be bigger than whatever is off the diagonal over here. And once you satisfy that criteria, you can be able to tell that you have really satisfied the criteria for discriminant validity. Does it make sense now? Does it make sense? Or we are still lost?
Yes, Doc.
Yes.
No, Doc.
Yes, Doc. We are good.
Are you sure? Because Loretta says she's not good.
No. Doc, when we check what is on this diagonal,
yeah,
let all the figures that are not on the diagonal are lower than what is on the diagonal.
Yes.
So how do we interpret that situation?
No, all of them, please don't read this one. Don't read the mean and the standard deviation line. Please, are you okay? Are you there?
Okay. Yeah.
The mean and the standard deviation are not part of, please.
Okay,
they're not part.
Okay.
So just read the constructs, right?
Okay.
And the interconstruct correlation. So you see that each of the interconstruct correlations here is lower than all the figures on the diagonal. Can you see that?
Yes.
Good.
Yes, please.
So that tells us that we have satisfied discriminant validity. The inclusion of the mean and the standard deviation is mainly optional. Like I said, it's a matter of style and the outlets that you are using to publish your work, right? So you can decide to include the mean and standard deviation or not. It doesn't affect the Fornell and Lacker criterion in any way, right? The main elements of the criterion are from 1 to 6, the variables that are there, the correlations between them, and then how they relate to the AVEs on the diagonal. So in the event that you decide to go with finding the square root of the AVEs, you leave the interconstruct correlations alone and you compare the two. And definitely you have to make sure that whatever is on the diagonal is bigger than what is off the diagonal. Likewise, if you decide to go reverse and square the interconstruct correlations, you leave the AVEs alone. But again, in that instance, what is on the diagonal still has to be bigger than what is off the diagonal. Please, does it make sense now?
Yeah, yes, it does. But the question is, what happens if we have a situation where the items there, one of them is higher than what is on the diagonal, the AVE?
Good. That means that you are having issues with validity, either convergent validity, right, or reliability. So you have to go back to the model and do some pruning. Are you with me? That is why I always recommend that if you have not satisfied all the criteria for a particular level, don't jump to the next level. So if you have not satisfied all the criteria for convergent validity, don't even attempt testing for discriminant validity because it will not work out. The variables will expose you. Does it make sense?
Doc.
Yes.
Doc, can I please take you back a little?
Yes.
Did you say that when you're doing the pruning, for each of the constructs you are testing, at least you should have 2 variables on each of the constructs? You can't go below 2.
Yeah, you can't go below 2. Because one of them is the marker variable.
Okay.
So in presenting output from AMOS, you will see that there's always a variable that has a fixed t value.
Yeah.
Good. And then there's another variable that takes inspiration from that marker variable. So the marker variable alone cannot carry the whole team. He needs at least one other variable to support.
So Doc, quick one. What if like what you're showing us now, advertising, word of mouth, publicity, affective trust, cognitive trust, and attitude.
Yeah.
What if when you're doing all the pruning, you keep pruning, and then maybe with attitude, you still have to go further than that, and maybe before your model will fit.
Further than that, in what sense? Like you prune everything off.
Yes, so let's say you get to attitude, you are left with 1. Do you have to take out that construct entirely because it is weak?
Exactly. So it means that in terms of the data that you have, that construct does not belong in the model.
Okay. Okay.
Good. Please, does it make sense now?
Yes, please.
Awesome. Awesome. So that is it for the Funnel and Lacquer criteria, right? Now the STMT is a bit more straightforward. Once you are able to run the analysis, all you need to be able to check is whether the ratio of correlations between them is less than 0.85, or for some, depending on the source you are using, they use 0.9, right? So once you run the STMT analysis, you put everything into a table form, similar to the Funnel and Lacquer criteria, and then you just look through. Are they all below 0.85 or are they all below 0.9? If so, discriminant validity has been satisfied. See how straightforward this one is?
Okay.
That's why it's an improvement on Funnel and Lacquer. So if you are running STEM analysis right now, you can decide to go with either Funnel and Lacquer or HTMT, or to be able to show your dexterity or to be able to prove your discriminant validity beyond reasonable doubt. You can use both. I have done that before. I've used one and then I've used both, and both of them have been accepted, right? So it's up to you, being the researcher, to decide what direction you want to go in. So that is it for the 2 tables for discriminant validity based on HTMT analysis and the Funnel and Lacquer criteria, right? So like I said, in our practical sessions, we will go about how to practically compute each of these tables, right? So we will learn how to run the tests for the Funnel and Lacquer and then for the HTMT, right? And then we will present these tables in real time. So everybody will get to try their hands on it. Now, after we have satisfied discriminant validity, the next thing is model fit indices. Now, with variance-based SEM like PLS, they don't bother themselves too much with model fit. As long as they have a good R-square and the effect sizes are good, the relationships are significant like they're supposed to be, they just go ahead and don't bother so much with model fit. But with AMOS, and specifically covariance-based SEM, we care a lot about model fit indices. And because of that, we break down the indices into different groups to be able to determine the different levels of fitness that the model can have, right? So a good model fit is a necessity when you are testing a model using covariance-based SEM, especially in AMOS, right? Because if your model fit is not good, it means that the model that you have is not good enough to explain what is happening in terms of the phenomenon in the data that you have gathered. So it is very important to have specific model fit indices. And to be able to ensure that your model is a good fit for the data you've gathered, we recommend picking at least 2 indices from the different levels of model fit. So we have three main levels of model fit. We have the absolute fit, the comparative fit, and the parsimonious fit. Right? Now we'll take each of them one after the other and just see what they are all about. Right? So the absolute fit indices contain indices including the chi-square. Those who have used STEM before. The chi-square and the chi-square degrees of freedom ratio are a typical example of model fit indices. Right? So what is the cutoff point for the chi-square degrees of freedom ratio? For those of you who have run SEM before. Chi-square degrees of freedom ratio, Gabriel.
Doc, I have not used the AMOS before, so I'm not familiar with the model fit indices.
Okay, good. Right, so that is a direct example of what I was saying with regard to variance-based SEM, that they don't really bother themselves much with model fit, right? But for covariance-based SEM, we care a lot about it. Okay, so Solomon, you are answering. You said it should be less than 3. Good. But I ideally like to work with less than or equal to 2, right? Since that is more rigorous. Please, are you with me? Hello?
Yes, Doc, we are with you, Doc.
Good. Right? So for the absolute or predictive fit indices, we like to keep the chi-square degrees of freedom ratio at less than or equal to 2 or 3, right? So in terms of absolute fit or predictive fit, the main criteria we care about over there is the chi-square and the chi-square degrees of freedom ratio. That is enough for us from that section, right? Now, when we come down, we come to the comparative fit indices. And here, like the name suggests, they are comparing the model that you have to a baseline model, right? So here, we are looking at more than one criterion, because one criterion is not enough when you are comparing your model that you have built to a baseline model, right? Which we can liken to the null and alternative hypothesis concept. So here, you need to pick at least 2 or 3 indices. And the very popular ones that we like using, especially in terms of AMOS, is the TLI, which is the Tucker-Lewis index, and then the IFI, which is the incremental fit index, and then the NFI, which is the normed fit index, and then the comparative fit index, which is the CFI. So you can pick 2 or 3 of these to represent your comparative fit and you'll be fine. And all of these have to be greater than or equal to 0.95 according to Schreiber 2008. However, there are other sources, right, in literature and in textbooks that have recommended cutoff points of 0.9. So in the event that you decide to use the cutoff point of 0.9, like I mentioned, you need to quote the exact source that you are picking your inspiration from. And in the event that you decide to use the 0.95 cutoff point, you need to indicate the source you are picking your inspiration from. So for this particular cutoff of 0.95, our inspiration is from Schreiber 2008. Please, does it make sense?
Yes, Doc.
So in quantitative data analysis, especially SEM, you cannot give outcomes and thresholds and cutoff points without giving us the source. Because here we are using Schreiber 2008 and we are saying 0.95 is our cutoff point. If someone comes and presents a contrary view, they can say we are wrong, right? But in the event that we are able to provide a credible source, we are right with our 0.95. And the same way, they will also be right with their 0.9 because they are able to also provide a scientific source for why they are using that threshold, right? Okay. Now, for the parsimonious fit indices, we don't really bother ourselves because they do not really have a major cutoff point. So usually you can just pick one from there and you are okay. The key components here in terms of fit is the absolute fit and the comparative fit. And parsimonious fit basically talks about parsimony. Please, who knows what parsimony means? Who knows what parsimony means? It's a big word with a small meaning. What does parsimony mean? What does parsimony mean?
Extreme unwillingness to spend.
Are you sure?
So, like, more or less like
parsimony.
Okay, I'm seeing small, few, miser, stingy. I'm thinking about it in terms of a human a human being. Let's think about it in terms of statistics, right? So in terms of statistics, when we talk about parsimony, we are basically referring to simplicity, right? How simple is your model? Your model has to be simple enough that, like Prince Yeboah is saying, it contains all the relevant variables that explain the phenomenon that you are studying. So if your model is unnecessarily complex and includes a lot of irrelevant variables, your parsimonious fit will not be good, right? So for instance, for parsimony adjusted for the goodness of fit index, it has to be closer to 1, right? So the closer to 1 it is, the better, right? And the parsimony adjusted NFI, which is the norm fit index, is very sensitive to model size. And that goes back to the inclusion of relevant and irrelevant variables. So if you have too many irrelevant variables, your parsimonious fit will punish you for it. So you need to make sure that the variables that you include in your framework or your model, again, are based on literature. That is the main source of relevance that you can have. And make sure that you are choosing variables that are direct indicators, right? So they have a high degree of relevance in terms of how they measure the dependent variable they are trying to measure, or perhaps in terms of how they relate to each other. The relationships there should be strong. So usually I recommend that we do not pick variables or models that are not coming from high-ranking journals, right? So for me, if a model is coming from a journal article that was published in a journal that is not very well ranked, I look at it with a lot of suspicion. Because that means that if you rely on it to be able to make some strong theoretical assumptions or conclusions, there's the likelihood that you may be found wanting, right? So in choosing variables, I encourage that you pick variables from published sources that are in well-ranked journals. So you can be able to guarantee that the variables you are picking indeed have been given the rigor in terms of testing that they deserve to arrive at the outcome that the article is presenting. Right? So for model fit indices, like I said, we pick the chi-square and the chi-square degrees of freedom ratio, and then we pick about 3 or 4 from the comparative fit, and then we throw in 1 parsimonious fit index, and then we are on our way, right? So Eric says, please give us an example of such high-ranked journals. Okay, so there are journal rankings that we use, right? We have Hazen's journal ranking, and then we have the ABS journal ranking, right? The Association of Business Schools journal ranking, which is currently the most popular one that we use in the business school. So in the ABS, they are ranked based on stars. So we have 4-star ranking, 3-star ranking, 2-star ranking, 1-star ranking. So any journal that is within these rankings is good enough, right? Some people will go ahead and include the Scopus database ranking. So any journal that is indexed in Scopus is presumed to have a good impact factor, and therefore some people like to rely on journals in those. Now, there are certain journals that may be in the Scopus ranking that will not be found in the ABS, because the ABS is a bit more strict in terms of its ranking and coming out with those lists. So for me personally, I like ABS ranked journals, because then I can be guaranteed that whatever variable I'm picking from whatever article or whatever skill I'm relying on or whatever theory I'm relying on has been adequately tested, right? And it has been published in an academic source that has a good impact factor. So I recommend the ABS journal ranking to you, Eric, and then the Hazen's ranking as well. I think those two are good, but ABS primarily. Tony Dadzi, you said no threshold for parsimonious fits. Yes, there's no threshold, right? But the smaller, the better. So you shouldn't have a parsimonious fit that is getting closer to 10. That's quite huge. So you want to keep it at a small point, right? You're good. So your PGFI, they are saying should be closer to 1, right? So it should be a similar application for the parsimony adjusted NFI, right? Or any other parsimonious fit that you decide to use. But like I said, we rely mainly on the absolute or predictive fit indices and then the comparative fit indices. So you realize that in certain publications, me, for instance, I don't report parsimonious fit in my articles because they are not rigorous enough in terms of measurement for me. I report only the absolute or predictive fit indices and then the comparative fit indices. And they are generally accepted all the time. So you can stick with that. Okay, any other question? Oh, we're good. All right, so let's move on. So now we have crossed the confirmatory factor analysis stage. We've done discriminant validity, convergent validity, and all those tests, and we have been able to prove that our model is good to go to the next phase. So at the structural phase, we are looking at a number of measures to be able to determine whether or not the hypotheses we have tested are significant or insignificant, right? So the first measure we look at is the standardized path estimates, or the beta values. Now in AMOS, they'll provide you with both the standardized and unstandardized estimates. But we rely on the standardized estimates to be able to make our conclusions, right? So the standardized estimates usually have to be greater than, right, or equal to 0.5. That's it for the beta values, to be able to see how strong they are, right? And these have to be significant. Even though you can have path estimates less than 0.5, but path estimates less than 0.5 are generally considered to be weak. So if you have a path estimate of say 0.4 or 0.3 or 0.2, then it means that the relationship between those two variables are quite weak. Now, the beta value is not significant unless you can be able to test it with the p-value to see if that particular estimate is either significant or insignificant or worth relying upon, right? So generally we use the p-value of less than or equal to 0.05, right? Which is the 5% significance level. So in AMOS, for instance, if you want to be able to see the significance level, most of the time they are represented using stars. So if you see 1 star, it represents a p-value of less than or equal to 0.05. If you see 2 stars, it represents a p-value of less than or equal to 0.01. And if you see 3 stars, it's an extremely high level of significance, which is represented by a p-value of less than or equal to 0.001. Please, does it make sense? Does it make sense?
Yes.
Good.
Yes, it does.
So that is it for the
Yes.
significance, right? Now, even before you look at the p-value, the t-values or the CR values can tell you whether or not a relationship is significant. For instance, any t-value in a two-tailed test, right, which is 1.96 and above, represents a significant relationship. So even if you don't look at the p-values and you see the t-value and it's 1.6 or more, then you know definitely that relationship is significant, right? And that is it for a two-tailed test. If it's a one-tailed test, then we are looking at a t-value greater than or equal to, I believe, 1.67, right? But generally for the kind of relationships that we test in terms of objectives and social sciences, we often rely on two-tailed tests, right, instead of single-tailed tests. And again, you can see that I am using sources to justify all the thresholds that I'm providing. Please, can we see that? So for the path estimates, we are justifying it with Hare et al. For the t-values, we are justifying it using Hare et al. For the path significance or the p-values, we are justifying it using Hare et al. And again, at the structural phase, once you are done presenting all these, you also have to present the overall model fit indices, right? Which we are justifying using Schreiber 2008. This doesn't make sense?
Yes.
Good.
Yes, Doc.
Good. Right? So at this point, you would have been able to test your direct relationships, right? This variable has a direct relationship with this. I think let's use this basic conceptual model as a reference point. So this conceptual model is basically about online repurchase intention, right? And it's basically trying to test the variables that influence whether or not someone who buys a product online will come back and buy again, like it's thinking of coming back to buy again, right? So here we have a number of independent variables, including security and privacy, which is not only just an independent variable, but it's also a mediating variable, which we'll get more into very soon, right? So here we are talking about the fact that other return and handling policies, timeliness of delivery, delivery condition, and security of privacy all have a direct causal relationship with online repurchase intention. So we will be able to test this relationship at the structural phase using hypothesis tests. And by the end of the structural phase, we'll be able to determine whether these direct relationships are significant or insignificant, right? But beyond that, we cannot test anything else unless we apply another form of statistical technique, So even though security and privacy here is both an independent variable and a mediating variable, at the structural phase, we can only determine the direct relationships. So to be able to test the mediating effect of security and privacy, we need to go on and test what we refer to as a mediation analysis. And this is an optional stage in the sense that some people will stop at hypothesis tests and establish the direct relationship between their variables and move on, right? Whereas others, because of the way their framework is designed, have to move beyond the structural phase of testing just the direct relationships and go ahead and perform additional analysis to be able to determine other relationships like a mediation relationship, or perform a multi-group analysis, or perform a moderation test, right? All of these, like I mentioned in the beginning, are dependent on the objectives of your study. So when you know the objectives of your research, you know the kind of analysis you need to be able to perform to address those research objectives. Please, I hope that makes sense.
Yes.
Yes.
Good.
Yes, Doc.
So assuming we want to move beyond the structural phase and test what we call a mediation analysis, right? We will go into the realm of mediation. And here, mediation occurs when an independent variable is postulated to exert an effect on an outcome variable through one or more intervening variables. Remember, I mentioned the fact that the mediator inserts itself or intervenes in the relationship between the dependent and independent variable. So a mediation occurs when we observe this kind of relationship. And with that, we can go ahead and test a mediation analysis. So there are two main testing methods for mediation. The first one is the causal steps approach by Baron and Kenny, 1986. And the second one is the product of effects approach, right? It was postulated by Preacher and Hayes and is underpinned by what we refer to as bootstrapping. Because I hope you've heard of bootstrapping.
Yes.
Okay. So in a typical mediation model, you will have a number of variables, right? Now, at its simplest form, a mediation model will contain an independent variable, a dependent variable, and a mediating variable, right? Where you will have direct effects and then an indirect effect going through the mediating variable. Please, do we see that?
Yes, please.
Good. Now, at a more complex level, we can have what we refer to as a serial mediation, where we have more than one mediator. So here we have a number of direct relationships and at least two indirect effects, right, in the same model. So we can go from X through M1 to Y, X through M2 to Y, and then X through M1 to M2 to Y, right? So this is a more complex, higher order form of mediation, right? And here the two mediators are purported to have a relationship with each other such that one is supposed to influence the other. Whereas in a parallel mediation, even though we have the two mediators, they are not related to each other in any way. So both mediations are happening simultaneously in a parallel nature in the same model, right? And there's a way too that we test this particular type of mediation. So once again, depending on the objectives of your study and how your framework is designed, you can either go for a simple mediation, a serial mediation, or parallel mediation. Each of them have rules and regulations that you have to follow. But for the purposes of this course and discussion, we will focus on dealing with the simple mediation, right? Once you understand the simple mediation, it's easy to build upon and understand and appreciate the other forms of mediation. So, as I mentioned earlier, when you test the mediation, being that you are testing a simple mediation model, there are three main outcomes you can have, right? You either get no mediation, meaning that that mediator that you propose does not mediate the direct relationship between the independent and the dependent variable in any way. Or you can get a partial mediation, meaning that the mediator plays its role as a mediator by inserting itself in the relationship between the dependent and independent variable. But at the same time, regardless of the presence of the mediator, the independent variable also still has a significant effect on the dependent variable. So the presence of these two relationships, being the direct relationship and the mediating relationship, leads us to what we refer to as a partial mediation. So in a partial mediation, you have a significant path both between X and Y, which are the dependent and independent variable, and a significant path from X to Y through M. However, if we don't get a partial mediation, we get what we refer to as a full mediation. And the full mediation here refers to where, as soon as we decide to test for the mediation, the direct relationship between the dependent and independent variable becomes insignificant. So it means that with the mediator, the only way that X can get to Y is by going through the mediator. And therefore, we have only one significant path, which is X to Y through M. And the path to X to Y becomes insignificant. And here we talk about the fact that we are experiencing what we refer to as a full mediation. So at the end of any mediation analysis, you can either get no mediation, a partial mediation, or a full mediation. Please, does it make sense?
Yes, please.
Yes, Doc. Doc.
Good. And all these have to be indicated in table form, right? So there's a separate table for mediation analysis. Now, I mentioned that there are two approaches to testing for mediation. We have the causal steps approach, and then we have the products of effects approach. And the causal steps approach is more of an outmoded approach where there were a number of steps you had to follow. And the satisfaction of one step allowed you to progress to the next step. And the proof of mediation lied in your ability to prove each of the steps from step 1 to 3. So step 1 involved, first of all, establishing a direct relationship between X and Y, right, which is part C. Then once you establish that, you need to be able to establish a relationship between X and M, being the independent variable and the mediator. Then once that is significant, you need to go ahead and establish a relationship between the mediator and the dependent variable, which is M to Y, right? So mediation is said to have occurred, right, when the association between the independent variable and the dependent variable, right, after controlling for the variance shared between the mediator and the dependent variable, which is shown here in this part, the C with the apostrophe next to it, right, shown as part C is significantly less than part C, which is the direct relationship, which we see here, right? So for mediation to be established, it means that when you introduce the mediator, the part C that was existing between X and Y must become diminished, meaning that the mediator's presence has inserted itself into the relationship and has weakened whatever relationship existed prior between X and Y. Abdul Karim, you said in a parallel mediation, is there a possibility of having full mediation on one hand and partial mediation on the other? Yes, there is a possibility, because both the mediators do not affect each other. So there's a possibility you can have a full mediation on one hand with one mediator and a partial mediation on one hand with the other mediator. I hope your question is answered. Okay, so this is one of the main reasons why the causal steps approach became outmoded. And it was mainly because of the fact that there may not always be a relationship, right, between X and Y to be mediated. Sometimes there may not be any relationship between X and Y, but when you bring M, X will have the power or the ability to influence Y through M. And because of that, people started exploring other ways of testing for mediation other than the causal steps approach, because it defeated the whole purpose of having an indirect effect on a dependent variable through a mediator, right? So in works what we refer to as the product of effects approach. So when you get the slides, you will see that we talk about the various critiques of the causal steps approach, which include what I just mentioned, right? And it involves the fact that there are several situations where mediation may occur in the absence of a significant relationship between the independent and dependent variable. And based on the causal steps approach, if you can't establish a direct relationship, it means you can't go ahead and test for mediation at all. Which means that if there's even a phenomenon there to be studied, you miss out on it, because there was a fundamental step, being the direct effects between X and Y was not proven, right? So the indirect effect approach to the product of effects test of mediation was propounded to help us to go ahead and test for the indirect effect in the event that there's no direct effect between X and Y. And that is how come the product of effects approach is now the more preferred approach to testing for mediation. Now, the product of effects approach uses what we refer to as bootstrapping, which helps us to extrapolate, right, our sample size several times to be able to obtain a larger sample to enhance or amplify the outcome of the test that we are running, right? So the software runs a complex algorithm, right, which can be explained in a very basic form. So bootstrapping basically treats the sample in your data set as a quasi-population, right? And using replacement, it is able to replace samples several times over.
Is a thing green?
Right? So you realize that when we run the mediation analysis in AMOS, we can determine how many times we want this to be repeated, right? And you can request anywhere from 1,000 times to 5,000 times, where it would extrapolate and resample and come out with about 1,000 to 5,000 different samples in which it will test the same model. So once it is done testing this based on the sample you have specified, be it 1,000 or 5,000 different samples, it will come out with a set of results that are bias corrected, right? So when we get to running mediation analysis in AMOS, you will see that we always go in to look at the bias corrected confidence interval to be able to actually determine how the end result of the bootstrap predicted whether or not there was a mediating relationship between this mediator and how it is intervening in the relationship between the independent and dependent variable. Now, like I said, a lot of these technicalities are complex, right? But you need to be able to appreciate the underlying concepts and issues to be able to appreciate what will happen when you are running it practically using the software, right? So indirect effects are possible to test using the product of effects approach, mainly because of the limitations of the causal steps approach, which does not help us to be able to test indirect effects in the event that there's no direct relationship between the dependent. So when we reach the mediation analysis stage, we will be testing using the product of effects approach, right, and bootstrapping. Awini, you said what's the difference between bootstrapping and blindfolding? Awini, that's your homework. Now that you understand what bootstrapping is, kindly go and find out what blindfolding is and then come and tell us the difference. Right? Because now you know what bootstrapping is. So if you are able to determine what blindfolding is, you can easily compare and tell us wherein the differences lie between those two. Right? Okay. So like I mentioned, we will go through the practical demonstration of each of these techniques we have talked about, starting from the two-step approach. So we will do a practical demonstration of the measurement model where we are conducting the confirmatory factor analysis, the structural model where we are conducting the path analysis, and then a demonstration of a mediation analysis using the bootstrap technique. We will do all these using SPSS and AMOS starting next week. So there's a basic data set that I'll be using to do the demonstration. I'll do my best to share the data set with you so that you can be able to practice alongside. And that data set will be based on the framework that I have presented in the slides, right? This particular framework, this one. So it's a simple mediation model that has various factors that are purported to influence online repurchase intention. So these are our independent variables. And then we have security and privacy as a mediator. Now, based on what we learned about the characteristics of SEM and why it is important for our purposes as social researchers, you can see that there are several direct relationships intertwined and presented in this model. Please, can we see that?
Yes.
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 Good. Now with SEM, we can test all of these at the same time and get results for all of them, taking into consideration how they react in the presence of each other. Whereas if we were using a multiple regression, we will have to do it path by path, individually, and it will not be able to account for how they all react to each other in the presence of each other, right? So SEM is a more comprehensive technique that helps us to come to a more conclusive appreciation of the phenomenon that we are studying and how that phenomenon actually plays out based on the data that we have gathered, right? So with that, we've come to the end of the theoretical portion of the whole SEM analysis thing using SPSS and AMOS, as we will be practically demonstrating in the coming weeks, right? And with that, we've come to the end of our session for today. Is there anything that anyone wants to ask or that they require clarification on? Yes, Nia, you go ahead.
Oh, please, how do we get the slides?
Okay, so I will try my best to make it available to your class rep, or I'll send it to Dr. Ohenia Sari so that he can be able to use his means to circulate it amongst you.
Okay,
so I'll either email it to Doc or I'll give it to your class rep. I think I may do both, or preferably send it to Doc. But you definitely get the slides either way.
Yes. Okay. Okay.
Well, Doc, please, how can we get a video?
The video, like I said, the email has limitations, right, in terms of file size. So I have a YouTube channel where I post all my videos. So you can go to the YouTube channel and then download the video when I upload it. So as soon as it's uploaded, I'll send you the link, and then you can just download it straight from there. And it saves us the stress of having to share it via email, where because of the size, it will go to OneDrive and it will become all those complicated things. Right?
Okay, okay,
Yes.
thank you.
You're welcome. Gabriel, you said, where is my office? You want to visit me? Hey, please, they said we should stay away from our offices as much as possible and work remotely. So I'm currently working remotely. So if you want to have a discussion, we can schedule a virtual one, and then we can discuss whatever it is that you want to discuss. But for a face-to-face meeting, I can't guarantee we can do that anytime soon. But my office is generally in the graduate building. I'm on the second floor of the graduate building during normal times. That's where you will find me. But currently we are in abnormal times. So we will have to schedule something virtual. Ralph, you said, is there any book I may recommend for you to gain more understanding? Especially those of you who may not have prior ideas. Okay, so I think you were late for the lecture. In the beginning, I introduced you to my book, right? So this is the second edition of my book. It's called Structural Equation Modeling Made Easy. It's available for sale on Amazon, and it's also available at Kingdom Books. So it breaks down all the basics of the issues, how to perform the various analytical techniques using SPSS, AMOS, and then Excel where necessary. And then you can also get here a towel for an explanation of some of the basic concepts, like the cutoff points and others. And then you can use literature, like journal articles, to help you with other information too about how to present your tables and stuff. But the most basic text I will recommend to you is Structural Equation Modeling Made Easy, because it is written for the basic mind when it comes to STEM analysis, right? So I'll recommend my book to you. Okay, how much is my book? Is it 150 Ghana cedis? I believe so. I think it's around 150 Ghana cedis at Kingdom Books. So when you go to Kingdom Books on main campus, you'll get some there. Benjamin, you said you think having seminar with you in year 2 will help you a lot. You have to talk to Dr. Ohenia Sari about that one, right? Since he has made all this possible. So when you have some thanks, give it to him. He's been advocating for this for a long time for you guys. So you can thank him and then liaise with him on how to be able to help you in your subsequent years, year 2 and year 3, and see how best he can help you get the additional support you need. But I think it's a great idea, Benjamin. So we can take it up with Doc. Okay, Edward, you said AMOS version 23. Yes, it will do, but you may not be able to use some of the plugins, because some of the plugins we will be using are for version 24 and higher, right? So you may not be able to use some of the plugins. And for most of the things, you need plugins to do them. But then for some of the techniques too, there are manual versions. So I'll teach you both the manual and the plugin version where I can. Akute Azu, you said, is the book available in PDF? No, there's no ebook version at the moment. I'm working on producing the ebook for the 3rd edition, right? Which will come out somewhere later this year. Prince Bar, please go ahead and ask your question.
Madam, good evening. Prof, thank you very much for the presentation. I wanted to ask this question that after going through the structural equation modeling, it seems that it's based on the variance and covariance analysis of the observable construct. But what if I'm interested in analyzing the means of the observable construct? How do I go about it? Or
then you have to use another technique.
Okay.
Right. So like I was telling you, you need to know the techniques that are available. That's why Dr. Hinasare is doing his best to expose you to as many as he can using different software so that you know your options. Because when you know your options, once you formulate your research objectives, you know which technique will best fit to help you achieve your research objectives. Does it make sense?
Now, what I intend to ask is that can you apply SEM to means instead of the covariance variance?
No.
Okay. Okay.
SEM is based on covariance or variance.
Okay.
Right? Yeah. So if you want to use the means as your basis of analysis, you have to look to another technique.
Okay. And then the last one, under the indirect effects, you talked about the bootstrapping, and in terms of the products, you multiply. But why don't you add instead of multiplication? I was a little bit confused there. Under the bootstrapping, page 38.
Remember I talked about the fact that bootstrapping does resampling.
Okay.
So it's extrapolate. When you're extrapolating, what are you doing?
You are increasing the sampling more or less?
Yes, but no, you're not doing so by adding.
Okay.
You're multiplying.
You're multiplying.
Okay. All right. All right. Thank you.
You're welcome, Prince. Please, anything else? Otherwise, we can call it a day and then meet back here again, God willing, next week to start with our practical demonstration.
Thank
Okay,
you.
Patience, you're welcome. All right. So on that note, I'd like to wish you all the best. I wish you a blessed week. I wish you success in all your endeavors for the rest of the week till we meet again on Monday. All right.
Bye-bye.
Goodbye.
Bye-bye.